Friends, in this video I explained how to draw shear force diagram and bending moment diagram for a simply supported beam with linearly varying loading. Beam of length L is shown in this figure. Here the supports are hinge support and roller support. Hinge support means movement in x direction is restricted. Movement in y direction is restricted. Roller support means hinge movement in x direction is restricted. And in addition, hinged fixed support means movement in x direction and movement in y direction is restricted, and moment in z direction is restricted. For the given beam, we drawn the free body diagram. We removed the supports and we introduced the reaction forces. For hinge support, 2 reaction forces, and roller support, 1 reaction force. Here the loading is varying linearly, so it is a function of x. Before solving this problem, we have to understand what is a loading diagram, what are all the things we can infer from the loading diagram. A total distributed load acting on any segment is the area of the loading diagram of the segment. Moment on any segment is the area of the loading diagram in the distance of the centroid of the diagram. Here the beam of length L is shown here. So first we have to write equation of the line. As I mentioned earlier, if area under the loading curve is the total load. So we have to recall what we learnt in mathematics. So area under the curve is nothing but double integration of dx into dy. Here the limits varies from 0 to L, that is x limits, and q limits varies from 0 to wx by L. How do we arrive wx by L? Here we know the line equation equal to y equal to mx plus c. M is nothing but slope, c is nothing but intercept. How much this loading line shifted from the origin? That is 0. Slope is nothing but tan theta, that is vertical component divided by horizontal component, w by L. Hence we got the load, double integration of dx into dq. X limits varies from 0 to L, q limits varies from 0 to wx by L. So I integrated 2 times, and what we get is half into w into L. This is nothing but area of a triangle, half into b into h. So using the equations of equilibrium, we write RA plus RB equal to half into W into L. So, to solve RA and RB, we need one more equation, that is moment equilibrium equation. So we are going to take moment limits varies from 0 to x and 0 to wx by L. So we got total load is equal to wx by x square by 2L. Next we have to find x bar. X bar equal to 1 by a double integral of x into dx into dq. Already we calculated the A load. So here we integrated 2 times. We got x bar is equal to 1 by A load wx cube by 3L. Why we kept 1 by A load as it is? To simplify the mathematical steps. Here we are having A load divided by A load. So both will get cancelled. Hence we kept as it is. Once we got the moment equation, which resembles a cubic parabola, it means ax cube plus bx. Variation of moment equation is nothing but shear force, and our shear force equation resembles a parabola. It means Vx equal to ax square plus c. Next we are going to calculate the maximum bending moment. To get a maximum bending moment, condition is variation of moment with respect to x is equal to 0. That means shear force equal to 0. At x equal to L by root 3, shear force is 0. And once we substitute the x equal to L by 3 in moment equation, we will get the maximum moment. That is WL square by 9 root 3. So our mx equation is x to the power of 3. Our Vx equation in x to the power of 2. So here we drawn a freehand sketch of shear force diagram and bending moment diagram. If we plot this mx equation for different values of x and Vx equation for the different values of x in Excel or MATLAB, we'll get a nice curve. Thank you.